So here we're going to tackle a specific kind of derivatives problem. It's called a rate in, rate out problem. And it's exactly what it sounds like. So here you can take a second to read the text. The problem is about people entering and leaving a store. And this actually happened to me today, where I had to wait outside the UPS store because of COVID restrictions, right? So the way this works is we have one function that describes people going into the store and one function that describes people going out of the store. So this is a really common context, and there's a couple other contexts we'll see as well. So for example, our Six Flags problem from the last video, that was a rate in, rate out problem as well. You often see these in terms of like things flowing into a tank. I'll draw you another little picture here. So here's my AP art level sketch. So I have water flowing into like a tub or a tank, and also there's a hole in the bottom, so water is draining out. And these rates may or may not be the same. So anytime I give you two functions, in a context like this, there's a decent chance we're dealing with a rate in, rate out type of problem. These show up in almost every AP exam as an FRQ as well. So let's jump into this example. So notice I'm given this function s, and then it's just a nice little polynomial function like this. And they tell you this doesn't matter for this particular problem. There's nobody in the store at 4 a.m. Okay, so we want a function now for the rate at which shoppers arrive in the store. So here we have the total number of people who have entered is s. So that word rate tells me to take the derivative of s, which is something you're good at this point. We're just going to use power rule. So that gives me 2t to the third minus 48t squared plus 288t is my s prime of t. So if s is the number of people who have entered the store, the rate of change of s prime, is the number of people entering the store. And then once we have our derivative, my next question is easy enough. So that we want the rate at which shoppers are arriving at the store at 7 a.m. Well, it gives me that we're starting at 4 a.m. That's t equals 0. So 7 a.m. is t equals 3. And I want then the derivative of s at 3. And I just plug in that value on my calculator. You get 486. And think about what the label should be here. 486, well, s was the number of shoppers. T was time in hours. So this is shoppers per hour, right? And I don't have to give it time because the time was already given to us in the question, but I should label for that for full credit. Okay, so that's the rate at which people are arriving at 7 a.m. Now here's where this problem starts to get a little bit more interesting. This is all stuff we could have done probably already. Here now it gives us the rate at which people leave the store. So again, draw a box around that word rate every time you see it. And it gives us this function L of t. And then again, we want the rate at which shoppers are leaving the store at 7 a.m. So 7 a.m. we still know is t equals 3. So now we have to be careful here. So it's important that we have read this carefully because L of t is already a rate. So previously S of t was just the number of shoppers. We did take the derivative to get to the rate. Here this is already done for us, right? This is already the derivative of the number of people who have left, right? So to find this rate, all we have to do in this case is take L of 3. So you have to do a little bit of interpretation here to do these correctly. And L of 3 is going to be 120 people per hour. And again, or shoppers per hour, I should say. And I just plug that into my calculator. Okay. And here's where the question gets really interesting, right? So is the number of shoppers in the store increasing or decreasing at 7 a.m.? So we have enough information to answer this question as long as we think a little bit hard about it. So let's go back to my little sketch. So we have people entering and leaving, and then there's some number of people in the store that we don't really know about, right? Well, now we have a little bit more information about how they're entering and leaving. So in my sketch, S prime of t describes them entering, right? That's the rate at which they enter. And L of t describes them leaving, right? So how to figure out how this is changing, the people in there? Well, it's going to depend on how fast people are leaving and how fast people are entering, right? So what we could do is we could say something like this, right? So we could say the number of people entering at 7 a.m., S prime of 3, is bigger than the number of people leaving at 7 a.m., L of 3, right? And our result backs that up, right? We have 486 versus 120. Well, if more people are entering than leaving here, we could say, so the number of shoppers is increasing. And we'll give it time at 7 a.m. Okay? So this interpretation, this is really the heavy lift of this problem, right? So we want to compare in versus out. That's how we tackle these. So for example, in our little bathtub problem here, if my in, the water coming in, is faster than the water going out, the water level will be going up, right? Where if it was the other way around, the water going out was faster than the water coming in, my water level will be going down. So that's the logic here. So my total is decreasing if, well, out is bigger than in. My total is increasing if my in is bigger than out. So this is not rocket science here, but it can be hard to figure this out in context. For justifying these, we want to say our y, so our number of shoppers, is increasing or decreasing at our specific t, so at 7 a.m., because, and then my justification is an inequality comparing the two functions. So because out is bigger than in, or in is bigger than out.